we continue our discussion on the base classification rule. So, to quickly review what we have studied so far, we draw the class conditional distribution, that is probability that if I know the class is ILSA, what is the probability that the fish has a length L, similarly for tuna. And I found that the optimal decision boundary was at the intersection of these two points. So, one problem with this approach is that it will this curves may be biased depending on where we take our population from. To compensate for that, we introduce a notion called a priori probability. So, a priori probability is probability that a randomly chosen fish belongs to class ILSA and a randomly chosen fish belongs to class tuna, no L involved. So, what I do is the following. In my original curves, let me show you the curve, I multiply this class conditional curve by this a priori probability, and I multiply this class similarly by this a priori probability. Okay. So, depending on what my if pH equal to Pt, the curve remains as it is. If pH is greater, this curve goes up, the other curve goes down, okay, and vice versa. So, I scale the class conditional by the prior, multiply it by the prior, and my new B star is the place where these multiplied curves intersect, that is my B star, say prime. Okay. So, let me write this down algebraically. So, I multiply the class conditional by the prior and I divide it by the probability of length being 2 feet, for example, in this case. So, I multiply the class conditional by the prior. What I get is something called a posterior distribution, meaning why posterior? You know the Bayes rule, which says that P of A given B into P B equals probability of B given A into P A. So, what I actually do is kind of bring this to the denominator of the right hand side, and make it P B. So, P A is the prior probability, a priori probability. P B given A is probability length equal to 2 feet given it belongs to class A. This is probability of a random fish belonging to class A. This is class conditional. So, class conditional into prior divided by P B. Note that this denominator, whatever class I take is same, it is independent of class. So, if I multiply both the curves by 1 by P B, both will equally scale. So, the intersection will not change. So, the denominator is kind of a scale factor same for both classes. Bayes rule tells me that this quantity equals probability of A given B, means probability of a fish being Hilsa given that its length is 2 feet. Okay. So, if I measure a length to be of a fish to be of 2 feet long, what is the probability it belongs to class Hilsa? How do I get that? I use the class conditional, that is distribution of length of all Hilsa fishes, multiply by the prior probability of a random fish being Hilsa, and I get the posterior. Okay. All right. So, this I have written down the definitions. Class conditional is this, prior is this, posterior is the product divided by a constant factor for each of the classes. So, what I actually do is that I find the posterior for both the classes. I find the posterior for Hilsa, I find the posterior for tuna, and instead of earlier I was drawing the intersection of two class conditionals, I just change that rule and I say I draw the distribution of the posterior probabilities. Okay, so, this is divided by some constant factor, probability of a random fish having length L irrespective of class. Okay. So, actually if I drop this in both side, I will still get the same intersection. And my B star boundary is now the intersection of these posteriors, not the class conditional as I had mentioned earlier. Okay. Because it takes better care of the bias in the population. It still has the minimum error. So, this is my definition of B star, it still has the minimum error. You can actually see by looking at the area, and this is what I will use. So, this classifier, since it uses this Bayes rule, is called a Bayes classifier, and it is actually sometimes called a Bayes optimal classifier, and B star is called the Bayes optimal boundary. Okay. It has the minimum error possible. Okay. So, I repeat my steps, what I had done, repeat my steps with these pictures. So, repeat my steps. So, what I actually do, let me look back a little. I collect a population, I draw this histogram for Hilsa, distribution of length, I draw the class, I draw the class conditional distributions for each of the class. Then I estimate the prior probabilities. How I estimate the prior probability? Just count in the population how many are Hilsa, how many are tuna. That fraction is my probability. That fraction is my probability. And what I do is that this last curve, after I find the prior, I multiply this curve. this I multiply by P Hilsa, this I multiply by P tuna, and what I get as a result is the reverse. P Hilsa given L, the posterior, P tuna given L. So, first compute this from the population, then compute this from the population, multiply them, ignore the constant factor in the denominator, get the posterior, repeat this for the tuna class, get the posterior, draw these two, I have drawn these two. Draw these two distributions, and same as before, set your B star to be the intersection of the posterior distributions. Okay. And it will still have the minimum error. All right. So, now okay, this is fine, this I call a base classifier. Let me make life a little bit easier for me. Instead of finding the intersection, solving these two equations and finding the intersection, I do the following. You make a observation that to the left of this B star, the Hilsa region, the blue curve, the Hilsa curve is above the pink curve, the tuna curve. And to the right of this distribution, which is the tuna region, the tuna curve stays above the Hilsa curve. The pink is above the blue, pink is above the blue. So, here pink is above the blue, here blue is above the pink. Okay. So, instead of finding out what the value of B star is, I can do the following. Given a new fish, you find out its probability of belonging, posterior probability of belonging to tuna, find its posterior probability of belonging to Hilsa, compare these two values, whichever value is higher, put it in that class. Okay. Whichever value is higher, find this posterior of one class, find the posterior of the other class, compare these values, whichever is higher, classify it into that class. So, I can sort of restate my base classifier as the maximum posteriori classifier. These curves are the posteriori probability curves, and my rule is put it into that class which has the highest posterior probability. The map rule, you follow the map principle, maximum a posteriori probability principle. It is same as the base classifier. This particular formulation actually helps me generalize this base classifier to more than two classes. Okay. So, suppose there are three classes of fish. In general, let us say there are k classes of fish. Okay. Let us say Hilsa and tuna and shark. I, using that base rule, I find this posterior, sorry, I find out this posterior, which is class conditional into prior for Hilsa. I find out the posterior curve for tuna pink, I find the posterior curve for shark black. Now, for a new fish, I measure it L. Suppose L is this value L1. I draw a vertical line L1. At that particular point, out of these three, whichever curve is the topmost curve, put that fish of length L1 into that class. Okay. So, basically follow the map principle, and this will give me the base classifier. Okay. So, this will give me the base classifier. Okay. So, again to summarize, if I have k class, take a population, find out the class conditional distributions for each of the class, find out the prior probabilities for each of the class, multiply them to get the posteriors, draw the posterior distribution for each of the class. For a new fish L1, classify it into a class which has the highest posterior for that value of L. Okay, map. Good. I think you have understood up to this. So, now you may ask the question that, well, you say that this is the best classifier, this has the minimum error. So, why not use this always? Why do I use decision tree or say support vector machine or something? Why not always use base classifier? The thing is that if I know this posterior distribution, if you know the class conditional distribution, then I can only find out the base classifier. Of course, if somebody tells me that this is the class conditional, I will definitely use the base classifier, but nobody will tell me what the class conditional distribution is. What I have done in this first example, by going to the market and drawing this curve, is only an estimate of these distributions. Of course, this estimate will be correct if I draw a large sample, but it is only an estimate, it will have an error. Okay, it is not exactly the unknown distribution, it is an estimate of the unknown distribution, there are estimation errors. Okay. So, that is the problem. So, even though base classifier is the best, as a precondition to applying the base classifier, you have to know the distributions. If you do not know the distribution, you estimate it, and that way there will be some error, and because of that error, it might not give you the optimal classifier. Okay. So, what I will do next, for one dimension I have seen that the decision boundary was a point L star B star. Suppose my classes are multivariate to bivariate distribution. So, instead of characterizing a fish only by its length, I measure the length as well as weight. Okay. So, any face is a point in any face is actually a point in two dimensional space, is a point in two dimensional space, some length value, some weight value. So, now if I take a number of tuna, they will have some mean length weight and there will be some distribution variance around that. There will be for hilsa also. Let us assume that these individual distributions are normal distributions, bivariate Gaussian distributions. Okay. So, how does bivariate Gaussian distributions actually look like? So, for example, if this is my L and this is my W, and if I in the z axis if I draw my probability, they look like bell shaped curves. If I project them, they will look like circles or ellipses. Okay. So, they will be like a bell over LW space or LW plane. Okay. So, I have one such bell for the tuna. Note that. So, what I am drawing here is actually the projection of the bell to LW space. I am looking from the top. This is a picture looking from the top. Similarly, I have a bell for hilsa, and these projections will either look like an circle if this bell is symmetric, or look like an ellipse if the bell is elongated more in one direction than the other. Now, earlier I said if when in the univariate case the boundary was the intersection between two distributions. But now if we put two such bells, their intersection is not a point, but a curve between them, okay, in LW space, LW plane. If we just look at values where these two bells intersect, I will get a curve. So, this curve is actually my decision boundary. What will work out is, if I know the parameters of this class condition of these posterior distributions and assume them to be Gaussian or normal distribution, how does this decision boundaries look like? What type of curve they are? Okay. You know, a Gaussian distribution, a normal distribution, is parameterized by two parameters, the mean value and a variance value, mu sigma. In the case of two dimensional bivariate Gaussians, the mu will be nothing but a two dimensional vector representing this center, a two dimensional vector, and sigma will be a 2 by 2 matrix So, this will mu will be a 2 dimensional L W vector and sigma will be a let me write it as capital sigma will be a 2 dimensional matrix where the entries are the following. The first entry is variance of L with itself, the second entry is variance of W with itself. So, if let me define what variance is. So, sigma roughly is if I have n samples, it is the variation of x from the mean square of that summed over all the x. So, if you take x 1, x 2, x 3, x n, okay. So, x I, if we each of these x I find how far it is from mu, take the difference, square it up, add it up over all n, take the average value of this squared error. It measures the kind of spread of the distribution, whereas mu measures the central location of the distribution. If I have a bivariate, it is not just sigma is no longer a scalar, it is a matrix. So, now what does the matrix look like? Matrix will look like, I am getting dirty. So, the matrix will look like, it is the sigma of L, mean value of length and variation of length of each piece from this mean value for tuna class or Hilsa class, mean value of W, the average weight of a tuna and how the weight of individual tunas differ from this average weight, square that up, sum that up, and then the covariances. So, covariance is a cross term, that means variation of length with respect to average W, variation of W with respect to average L, same thing, but the central are cross. Okay. So, suppose somehow by estimation or something I know the mean value and sigma value of tuna, I know mu t, sigma t, and I know mu h, sigma h. Then I want to derive the decision boundary as a function of mu t, mu h, sigma t, sigma h. Okay. If you remember the Gaussian distribution, next it takes this particular form. So, e to the power minus x minus mu by sigma square and then some constant term of sigma. Okay. So, this is how the probability of x belonging to this Gaussian distribution looks like. Okay. So, I will use that expression and I will derive under various conditions on mu and sigma what does this boundary look like. Actually, I will give you as an exercise, you consider two special cases. So, if the sigma is a diagonal matrix and unit diagonal matrix. So, basically these are unit spheres, each of them, both of them have same sigma and unit diagonal matrices and some value of mu h and mu t, some value of mu h and mu t. Then putting this thing, where does posterior assume class conditionals are same 0.5, 0.5 both sorry, assume priors are same 0.5, 0.5 for both. Where does the posterior distribution give at what values of, what is the locus of the values of x which give same value of probability for both the distributions mu t, sigma t, mu h sigma h. I am not writing the exact form, you should write it. So, where does these two equate, over which locus of x? That is my decision boundary by definition of the base classifier. Okay. So, we will derive it for different assumptions on mu and sigma, and we will see they have a nice geometrical form. So, with this assignment you should work out. I end today's lecture. I will continue discussion on this in my next lecture. Thank you.